Hey, chemistry, it's Thursday, April 9th, and we're on page 413. If you could work your way there, that would be great. Henry's Law. Henry's Law says the solubility of a gas in a liquid is directly proportional to the partial pressure of that gas on the surface of the liquid. And I've already told you about the idea that if you want to keep the carbon dioxide in the drink, that you're going to have to go ahead and put it in under pressure. And then if you want to increase the pressure, it's going to need to be more carbon dioxide that sits on top of it. So Henry's Law application is scuba diving. So when you go down under the water, every 10 meters or about 30 feet of depth in the water is the same as if you have another atmosphere of air sitting on you. You know how you go up 50 miles for all that air and it exerts pressure on your body? Well, you only have to go down 30 feet, 10 meters, to get another atmosphere of pressure. If you go down 20 meters, you've got 3 atmospheres of pressure because you got the one from the air and then you got the 2 from the water. And so when you get down there at higher pressures, it takes, when you breathe nitrogen and oxygen, of course. It takes that nitrogen and it pushes it into the bloodstream. Now, when you come up, you need to come up slowly. And when you come up slowly, it has an ability then to leave the bloodstream and go through the normal respiratory system into your tank, and you can go ahead and release that nitrogen from your blood that way. If you come up slowly and you level off, you wait for a little bit, then you go up a little higher, and then you level off, that's part of scuba diving. But if you come up rapidly and get up to a low pressure environment in the boat, when the stuff is still trapped in your bloodstream, that nitrogen will lodge itself in the joints as it's coming out of solution. And it doesn't come out through the normal respiratory system. Instead, it traps into the joints, like down here under the rib cages, and people bend over from the pain. So it's called the bends. And so you can die from the bends because when that gas comes out of your solution or out of the trapped joints, it can go ahead and get, it's still in the bloodstream, and it can go ahead and cause aneurysms or whatever they do when a gas blocks a blood vessel and doesn't allow the blood to pass. So it's a real dangerous thing, and they take them and repressurize them. And so it's called a recompression chamber. And they take you into a great big old thick metal coffin, if you please, repressurize the air around your body and push that stuff back into solution and get it out of the trapped joints that way, and then bring you back out slowly by easing off on the pressure very slowly. So I just thought I'd tell you that. That's the application of Henry's Law. More pressure means gases can dissolve better in solution. Page 414. Take a look at the 2 graphs at the top. What is the solubility of H2S, hydrogen sulfide gas dissolved in water, at, let's say, 10 degrees in temperature? Looks like it's about 3.5 milliliters of gas per milliliter of water. But what if you get warmer? How much gas can that water hold then? 2, and then down to 1 before it gets up to like 100 degrees. How about carbon dioxide? Does the amount of carbon dioxide that a milliliter of water can hold decrease as temperature goes up? Yeah, gases will leave as temperature goes up. Now think about that. If you were to put this Coke out on the front porch during the heat of the summer, wouldn't it get flat? What does flat mean? Flat means the gas is coming out of solution. Because the temperature of the solution is warming up, it drives the gas out because the gas particles get more active and become less dense, and it just comes right out of solution. It's the same with all those gases up there, except for oxygen, pretty much just straight line. So how about, oxygen has a very low solubility factor, by the way. And sulfur dioxide, you can see that on the next graph. It goes down also as temperature goes up. However, look at the bottom. Can you give me the solubility of KNO3, potassium nitrate, at 100 degrees? So go down across 100 degrees and go straight up, hit the graph and turn left. Is it around 240 grams of potassium nitrate? So solids, as the temperature rises, the solubility, the amount you can put in this case, 100 grams of water, the amount that you can put in there goes up appreciably for some of those solids. So an increase in temperature allows solids to dissolve more in a given amount of solvent, and an increase in temperature allows less gas to dissolve in a given amount of solvent. Okay, skip page 415 because we've already discussed it. Go over to 416 and take a look at potassium chlorate, KClO3 on the table. Is it a positive 41.38 on table 5? KClO3 has a positive enthalpy of solution, which means as it dissolves in water, it releases, wrong. Positive means it takes in energy from the water, so the water gets cooler. It'd be great for a cold pack as it's dissolving in the water. In fact, a chemical cold pack is a real saturated solution of one of these inside of a water. And so you break the inner bladder and it spills into the outer bladder. And as it's dissolving in the outer bladder, it takes in or releases energy. And so this would be a good cold pack because it would take in energy from the water and cause the cold pack to get cold in order to make the dissolution process continue, dissolving process. Okay, so let's do a lab. And when we get done with that, we'll quit for the day. So I'm going to take about 20 milliliters of water. I have distilled water here. And I'm going to go ahead and measure it out with this good old graduated cylinder. I'm going to hold it up here where I can see it. Right there, 20 milliliters of water. I'm going to measure the temperature. By the way, we're going to try to get that value that's on the table. And the temperature of this water is 22 exactly. Now, this is something you would be doing, but of course, we're not in school. 22. I'm going to measure out about 3 grams of potassium chlorate. You know how I know it's potassium chlorate? Because it says it right there. KClO3. Yeah, I know that's not the right container, so I had to improvise. So we're going to take this and stick it on the balance. Well, turn it on. We're going to stick this on the balance, that little beaker. I'm going to push the tare button. Now it's 0. And we're going to get about 3 grams of potassium chlorate. .02 grams of potassium chlorate. Okay. The initial temperature, 20 degrees Celsius. KClO3, 3.02 grams. Okay. So let's go ahead and pour it in there and see how much the temperature goes down. Okay, so here we go. We're going to put that in. I'm going to go ahead and just stick that in here. We're going to stick it in this little sleeve that I've made for the styrofoam cup. And that's so you can contain the heat and not get any of the heat of the room. Now you can see all of that lab air right here on the side of this graduated cylinder. Some of that potassium chlorate stuck to the side on the way down. We are now down to 19. But it hasn't all dissolved yet. Oop, can you see there's still some on the bottom? I don't know if this is going to work. I usually use sodium hydroxide. Cool. And it is exothermic. You can see it on the table, NaOH, negative 44.51. It makes the solution get hotter. And it's very visible because it's negative 44. But this is positive 41, so it's supposed to make that go down quite a ways while it's dissolving. Down to about 18. The other dissolves pretty rapidly. So I'm taking up a lot of your time, your valuable time doing this. This is not going to work out because it's not all dissolved. Go too slow. So I'm just going to go ahead and go with it. Let's say it went down to about 17 and a half. 17 and a half, but it's not done, but that's okay. You'll get the idea. So we're going to go ahead and find out how much the water, how much heat the water gains. So the initial temperature was 20, and the final temperature is 17.5. So take 20 minus 17.5. What is that, about 2.5 degrees? You learned earlier in the year that heat is mass times temperature change times specific heat of the water. This is the water that we're dealing with. How much heat did it gain? Well, the mass was 20 milliliters, which is the same as 20 grams, because water's density is 1 gram per milliliter. The temperature change is 2.5. And the specific heat of water is 4,184 joules per gram to change 1 degree Celsius. So grams cancel, Celsius cancels. So how many joules? Let's go ahead and multiply that. 20 times 2.5. Sorry, I'm taking so long. Times 4184. Trying to do a little lab here for you. So that's 209,200 joules. Did I get that right? I'm going to do that again to make sure. 20 times 2.5 times 4184. Yep. Okay. Now the other thing we're going to deal with is how many, by the way, let's change that to kilojoules. Divide by 1,000, you're going to get 209.2 kBj. That's one of our pieces of information. The other piece of information is how many moles is 3.02 grams. So 3.02 grams of KClO3, 1 mole of KClO3 is how many grams of KClO3? Well, I happened to add that up before I started this. It was 122.548. I got that molar mass down to the gnat's eyebrow because I use these numbers off of here exactly because I'm doing a lab. And so now what we're going to do here is find out what that is. 3.02 divided by 122.548. 0.0246. Moles KClO3. And so if we take red divided by the green, it'll give us kilojoules per mole. And it's supposed to come up with plus 41.38, which doesn't look like it's going to, but that's all right. And this goes 8,489. That's pretty close to 41, 8,489. And the reason it's so high is because I didn't give it enough time to dissolve the whole thing. It would have gotten colder and colder. If it would have gotten colder and colder, it might have changed things. I'm not sure. Okay, so see ya. Thanks for hanging in there with